University of Gottingen, who will talk about elliptic boundary problems for edge-degenerate pseudodifferential equations.
Okay, thank you very much. Thanks for the introduction. Also thanks to Micah and his group for the organization of this beautiful summer school. And just before I start, so that is a summer school, so you're welcome to interrupt me if you have a question or something that's not clear. And I will try to explain things carefully. Of course, it's limited time, so yeah, I can just only explain that much. So I'm going to talk about the basic PDE problem, which is elliptic boundary problems, but in generalized setting. Yeah, and you will see why that is necessary. So the part what is new, it is joint work with Liu Chun of Wuhan and Wan Zhou of Nanjing, who is in the room. And okay, yeah, that's it. We can start. So here you see the outline, the plan of my lectures. We don't need to go through that. We will see all of that later. Okay. Yeah, so I will basically explain around these edge-degenerate elliptic boundary problems, but at the same time I use the opportunity to introduce you to techniques from singular analysis. Singular analysis, what is that? It is analysis on spaces with geometric singularities, using tools for microlocal analysis. Yeah, and these singularities could be conic points, edges, corners, and so on, but also boundaries. Yeah, and we are discussing here the case of boundaries. Yeah, and basically, a boundary you will see is a sort of an edge. Yeah, and so we will meet during the course. We will meet both cone degenerate and edge-degenerate operators. So just what is a cone? This is briefly explained. Now we have if you have a cone, it's something like that. So we have here some say closed manifold Z, and we have here the radial direction, which is a positive variable x. Then cone degenerate is an operator which is of that form, x, z, x, dx, and dz. We have here these totally characteristic derivatives. And in front of we have the factor x to the minus the order of the operator, m the order of the operator. Yeah, so for instance, you get that if you write the Euclidean metric in polar coordinates. Polar coordinates. Yeah, it is totally exactly of that form, and x is then again the regular variable. So and so what is an edge? The local model of an edge is basically a cone bundle. So we have here some variable y. It's a piece of Euclidean space, and then we have here a bunch of cones. Okay, like that. So now we have one variable more, and operators are going to be of that form. The x dx, x dy, dz.
Sorry, what is Z?
This is just here the link of the code. That is here some closed manifold. So if it could be sphere, torus, whatever you like. Yeah, that is yeah, so the degeneracies are of this form here. So the dy comes also with a factor of x. So now you see a particular case of a cone is just a half length, and that is the case. So basically, we are going to discuss the z is not any longer there. And this form so we are going to discuss, which I mean here we mean special classes of these operators. Yeah, so here sorry. Of course, it's also good. Yeah, so just here the z is just a point. Yeah, then we have a boundary. Okay. Good. Okay. So that I don't have basically to say all the time this result is to this guy and to them. I say just in the beginning. So the whole thing started with a paper by Kondratiev in '67, boundary value problems for elliptic equations with conic points of the boundary or something like that. So that was the whole thing started. Then there was a preprint that was never published, but circulated by Melrose and Mendoza. It is called totally characteristic operators, which means exactly that. Yeah. So I said Cohen degenerates is totally characteristic. Melrose later, so there was a book in '93 by Melrose, and basically he calls it B-calculus. Yeah, so there is another school sort of belong to, that is the school of Schulze. So he had also these co-degenerate two-dimensional operators, and there were earlier publications, but in form of a monograph, it was just in '91. Yeah. So and then he has basically edge-degenerate two-dimensional operators in an article of '88. Then this led to the edge calculus. Actually, the difference between Cohen and B, it is not that big. Yeah? So on the Cohen side, Schulze has this factor. Melrose doesn't have that factor. It just multiplied everything by x to the n, and says it's not that important. On the Cohen level, that is true. If you iterate stuff and you arrive here at edge-degenerates, then it becomes important. And therefore, I say this is Schulze calculus. Yeah, and then there was the monographs by Schulze of '94, '98, and if you want to learn that stuff, so it's here very detailed, carefully written. The book of 2008 is how to do that. Okay. Good. So in general, we're working on a compact manifold with boundary. The local model is the closed half space, and so basically the normal variable is called x, the one-dimensional variable. Oh, x, that is the t is x. It used to be t, it changed to x, and so that is type of x. So x is non-positive, and then we have y. The y's are the tangential variables. Yeah, and occasionally I will also use x to denote the linear point in x, but it will be clear from the context. Good. So I already told you what an edge-degenerate operator is. In these coordinates, near the boundary, it takes that form. Okay? And the A, as the important thing, is smooth up to x equals 0. Otherwise, it's just a simulation. So, and so I have a couple of exercises for you. You can discuss these exercises in this discussion session if you like. The differential operators with smooth coefficients are edge-degenerate. So this is direct generalization. Yeah, this is sort of if all you see is here, you have x, definitely dx, and you write it as x. Okay, so this is direct generalization, so the class of edge-degenerate operators is bigger. Okay, so why is it interesting to deal with such problems? First of all, as I said, we will not only have differential but also pseudodifferential operators. And here are two examples. So the fractionally defined Laplacian say with the Dirichlet condition in a bounded smooth domain in Rn is edge-degenerate. And if you basically know the theory, you can just read off what are sort of elliptic bounding problems for that operator. And then here's a second example, the Zaremba problem. That is one of these problems which sort of a benchmark test. So you have here our domain omega. We just divide it in the boundary into two parts, separate them by a smooth hypersurface, so hypersurface in the boundary, and we impose here the Dirichlet condition, here the Neumann condition. Otherwise, say we have the Laplacian inside. Okay? So then, how to solve that problem? So here the boundary conditions jump. So we expect some singularities in the solutions here, of course. And well, such problems can be handled with a technique I'm not going to introduce, a technique which is called boundary reduction. So you would use to a problem which is a pseudodifferential in the boundary. So it's well established if you have basically, let's say this here not there, and you reduce things for the Neumann problem to the boundary. And you do it by comparing it with a problem from which you already know that it is not only elliptic, but it is invertible. Yeah, this is a Dirichlet problem, and you can compare it also to the Dirichlet problem here. So you have the Dirichlet problem everywhere. Yeah, and so what you're left with is basically so the reduction ends up here. You just want the manifold with boundary, gamma n, and you also have this boundary. It's only the sigma, and then what you get is an elliptic edge-degenerate operator. Yeah. So when you have the calculus, you can start to deal with that problem. This reduction has been done in a quite decent application, but it shows an overload. But I mean, this reduction has been done before, but it proves that the resulting operator is actually. Okay, so what is now the main objective? We want to understand the analytic structure of elliptic boundary problems. And that category. So I don't care that much about specific problems. If you have general theory and you have a specific problem, you just need to check the conditions. Right? And the results. Yeah, and so basically, what is our guiding example is what is that? You have pseudodifferential calculus for dealing with boundary boundary problems, density coefficients are smooth up to the boundary. Remember, differential operators is probably smooth up to the boundary edge-degenerate. Same is true as you will see for two-dimensional operators. Under some condition. Yeah, and the crucial rule is displayed by this transmission property. I'm going to also do that. And then the generalization we have done here last month. This is what I call it. And that will use all that stuff. So, okay. That's what do we have to do? So the asymptotics, the solutions near the boundaries, we have certain asymptotic expansions in powers of x, so x was the distance to the boundary, if you like. And so basically, if you have smooth coefficients, yeah, then or we are working in the solar spaces, we have this theta series expansion. Yeah, this theta series expansion, the coefficients give you appropriate boundary conditions. Yeah, so basically, if you have the Dirichlet condition, you take the coefficient of x to the 0. If you have the Neumann condition, you take the coefficient of x to the 1 and so on. So now the change is that we don't have any longer integer coefficients, yeah, or natural numbers, but basically any exponent is possible. In addition, we could also have logarithmic terms. Yeah, we have to understand that, and then we can just formulate simple boundary conditions. Then we have to get this asymptotic information into our Sobolev spaces. That's like the standard Sobolev spaces, and you can just take traces, yeah, to a certain order depending on the given regularity. We need to do the same thing, but now for the new sort of asymptotics. And then we have, so I said for Gottingen-Morell's calculus, the transmission property is to play this rule. we need to find the correct replacement, and this is done, as I already said, this is done via the so-called once this has been done, then it is just the usual steps in organizing two-dimensional calculus. Composition has to stay in the calculus. The brick need the principal symbol map to say what's the ellipticity, parametric construction for the elliptic element, and ellipticity being equivalent to the Fred parameter. That's the usual problem. Okay? So here this first things, and then give you a bit more references, and then I'm almost done with the references. So if you want to learn about two-dimensional boundary problems, and so there is an article by Witt and Bell, and then there were very little monographs by Randall Schulze, their group, and then also in this monograph by Schulze, they reformulated things as an edge calculus. So edge-degenerate operators, in the way I'm going to use, they are introduced by Schulze. There was pre-runner by Randall and Schulze, another monograph, also variable. It's called Synchronics of solutions to problems or something. So then the construction of conormal symbols to need was by myself. After that, with Leo, we could do the one-dimensional case, which is just here, dimension x1. That's the co-engagement operator. Basically, the idea which helped us to solve. Last year, the Swiss European introduced these function spaces. It was the last missing step. So that was in a completely different context. Okay, we will on that now. Okay, so then, so we start with an example, and so I could do it in basically any dimension. Just I want to have nice formula, so I work in 3 dimensions. Omega is a bounded smooth domain, and we consider the we consider the derivative problem. Okay, and then we write that problem in the form. So we have some operator, I call it A, and A of U are, and this is of the data F and G, and this operator is of that form. So here we have the Laplacian, the positive Laplacian, and the minus sign, and we have the trace operator gamma naught, which is just the boundary. Yeah, we get such an operator. Yeah? And then it's well known that this operator is invertible, and of course, that operator, so here we have a column, so we get a row. Yeah, and here, so basically, K is the solution operator if F is 0, and if you only have the G. And this guy here in the left place is a solution operator if G is 0. And this is, for us, it is the most interesting part. It is of the form P plus G. And what are P plus and G? Okay. So we start with the free space solution. Yeah? So we take the Newton potential, we have just seen it in the previous talk. This is the convolution with 1 over z, essentially up to constant. That is the two-dimensional operator of order -2, everything fine. And then the first idea to solve our problem is just you start with something which is f is so this is P plus x and f. So f lives at omega, you extend by 0. You extend by 0, you let this operator p act, and then you restrict back to omega. Yeah? Then that is basically what we do. And the problem here is that we have basically solved your equation in the interior, but you sort of miss the boundary condition. The boundary condition is not the homogeneous one, because G is 0 for that part. Okay? So, and then basically we add an operator, G, to compensate for that boundary condition, which actually turns out to be smoothing in the interior. So this is basically an operator having an interior and a smooth kernel, but with a very specific singular behavior towards the boundary. And basically what we When I do, we want the GF restricted to the boundary of omega equals the negative of GF, is the boundary. Yeah, so then actually there is this G is found basically corresponding PDEs by the method of dimensions in certain situations. If you have a half space, you have a Green's function down here, and then up there, and then just add it, and, or you can just do this conflection stuff that if you have folds or whatever. Yeah? So that's the general thing. Yeah, and K is called the potential operator. I'm not going to discuss the structure right now. Okay.
So this can be used for boundary potentials.
Yes, that's sort of boundary of potential generalization. Okay. Let's now look at this boundary. Okay. So now we have one problem. Yeah, so we do this extension, and so we have, yeah, so if we do extension by 0, the singular support of E plus F will be in general the whole boundary. We have something which is, we start the F is smooth up to the boundary. We start with some F in infinity on omega bar. Yeah, and it places the F doesn't vanish, you introduce the singularity. So now your basically Q operators are Q local. So you will be having an operator is elliptic. So this in general, yeah? So the P plus F will also be boundary. And then the switch back to omega as an approximation. There's one algebraic condition which helps. This is transmission property. I'm too fast. Okay, sorry. I was next slide. So first of all, yeah. So the whole calculus, we get such rows, such columns, we get such rows, and then we fill up by two matrix, and we expect operators of that form. And then E and F, so we can have more than one boundary, and E and F are vector bundles, complex vector bundles for the boundary. And S turns out to be pseudo operator in this one. So you can also have vector bundles here, just for the scale case. Yeah? So in the last set of references. So there were work on these problems by GPS team in a series of paper in the 60s, and then the series of answers that one of by asking very for 73. So then, what did this step, he added the transmission condition. Yeah, so here the transmission condition is missing. And then, as I said before, this was nicely described and wrote by Michael Schulze group. And then Schulze actually just did one further step. He took Gottingen calculus and reformulated it as an edge calculus. That is what I'm going to use here. So there is basically Michael Schulze basically do things on the Fourier side of the Fourier transform. So they characterize all the symbols and blah 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 you get, and group does it on the X-space side. The characterize all the columns, and this quite heavy stuff. So there's actually the third approach. So if you heard about Lagrangian distributions, so you have Lagrangian distribution. It's a distribution which is given microlocally as an oscillatory integral. The case function parameterizes the Lagrangian submanifold of the code function bundle. and it has its singularities there, and then there's the form. So you can have also a bunch of subclinical submanifolds one to see finally many.
Sorry.
Yeah.
Can you agree?
T is the trace operator.
Okay.
T goes from here to here, and K goes from here to here, from the boundary into the domain. And the S is X here from here to here, into the boundary. And the E and F are there because you can have more than one boundary. So I should have said that. We discussed that. Sorry. I should have said that. So if you have differential operators, in most cases we are good with these column. And this has a reason. So if you just go back to our problem, so we have a Laplacian in that problem of X as a boundary condition. Let us suppose we have sort of that boundary. If you flatten the boundary, this is not any longer Laplacian, it doesn't. Yeah? Here we have our y variable. So our operator in that variables looks like that. Okay. So then there is, so if you have an elliptic problem, no, this was wrong. Then you have also elliptic boundary conditions, so conditions satisfying the Shapiro-Lobachitsky condition. And what is the Shapiro-Lobachitsky condition in that context? You do the partial Fourier transform in the tangential variables. So you get something, you get that operator, you get a family of ordinary differential operators parameterized by y, where y is non-zero. So this is some conjugation question. So and then you want to have this guy to become an isomorphism here. So you can just do it as a second order differential operator with constant coefficients. It's easily to find a fundamental system that is of that form. So now you see, this one is good. It is in that space. This one is exponentially growing, so we can just disregard it. But then basically we have a one-dimensional kernel. Yeah? And so you need sort of to kill that one-dimensional kernel, and you do it by adding an initial condition at x equals 0. And the way you do it, you get Dirichlet or Neumann condition or whatever. Yeah? And the point is, so why don't we have differential operators in general? Here's this K, this potential or co-boundary conditions, because these operators, it's easy to see they're always surjective. Yeah, so they can have a kernel, but they're always surjective. So there's nothing, so there is no co-kernel to kill if you like. Yeah, so basically the ellipticity of your main operator implies that all these operators are Fredholm operators. In general, they have a kernel and a co-kernel. You have to kill this kernel and co-kernel with boundary and potential conditions. But so that's always subjective, so that's no co-kernel, except for boundary conditions. For differential operators. As a rule, not always, there are exceptions. Okay, good. We expect to get something like that, and then I already started with the transmission property. And the transmission property is this. Maybe I should tell it to you in the bounded domain. So if you have a manifold with this boundary, yeah, it's just the average and become manifold without boundary, for instance, passing to the double. Then you take a second copy of the manifold with boundary and go along the common boundary. Yeah, and then this is X. And we have also this E plus extension by 0 and restriction back. And the transmission property is, which indicates this operator A plus, and you want it to map the functions which are smooth up to the boundary should become functions which are smooth up to the boundary. And this is guaranteed. This is actually if and only if by one algebraic condition on the full symbol of your operator. So you have, say, a classical operator. Well, it is just here, so A symbol of order n classical, so we have an asymptotic expansion, that is a homogeneous component. So thus I denote here by the j's component is of homogeneity m minus j, so I denote it that way. And then basically homogeneity is always positive homogeneity. Yeah, so if n minus j x by lambda beta, then this is going to be lambda m minus j, and then we have the same stuff here. Okay? But this is only for lambda positive. Yeah, and now you make a link between the positive and the negative side. Yeah, so basically going over to the other side, you get this factor here. And actually m might be here, might be even complex. Yeah, and so basically the best sort of case is if m is an integer, because then this factor is just negative 1 to the m minus j minus beta. And then it is sort of totally homogeneous. So you can just replace that here by, if m is an integer, you can just replace it by lambda. That is a transformation. Yeah? So if m is an integer, it is automatically both-sided. It doesn't matter whether you come from the inside or outside. If m is not an integer, in all other cases, it is one-sided. Yeah? In this case, it is written here. So for the case coming here, coming from the inside. But of course, you can just play the same game from the outside. So this is just one algebraic condition which guarantees this property. It's an if and only. It can be formulated in many different ways. That is one possible way. Yeah? So basically, the course was an observation made by Peter Model, and then he sort of took this what Witt and Eskin had done before, and then he came up with this calculus. Now there you have all. Going back to here, there you have all these mapping properties, and then you could just also characterize the operators. It's very complicated. I'm not going to do that. I just tell you what is the result. So I tell you what is the result after the formulation of edge-degenerate operators. Okay. So edge-degenerate operator. So if you have a pseudodifferential calculus, the first thing you need to understand is the symbolic structure. Yeah, what are the principal symbols? And as a rule, so you have an inner two-dimensional symbol, the usual one, and then every exit to infinity or every singularity is controlled by another principal symbol. That is the rule. In our case, we have a boundary, yeah, or we have an edge, if you like. Yeah, we get an edge or boundary symbol. So we get a second symbol. So if he writes the operator formally in that way here, we had it before, then we have the usual, the pseudodifferential symbol. We take here a leading component of the A, and then it's homogeneous of degree m, and in our special case here, we have an x psi, but we have an x is negative m in front of the just cancel. That is a principal symbol. And it lives on the cotangent bundle of x. This is your section 1. Then we get a second one, which is exactly, I've shown you here, this invertibility of these elliptic operators for this operator. This one. This operator, what is this? Yes, so for differential operators, I suppose that is a differential operator that is a family of differential operators in X along the inner normal. Yeah, it's our cone, indexed by points of the cotangent bundle over the boundary with a zero section removed. Yeah, so that is exactly what we had here before. Yeah, that is, so what do we do? So we just don't touch here this totally characteristic derivative. We freeze coefficients at x equals 0, and here we basically replace the differentiation with the corresponding curve. Yeah, this is exactly this guy here we had 4, 4, 4, 4, 4. And okay, so the point is, so that is an operator function, yeah, depending on y and eta, and it takes values in the cone-degenerate operators. So that is here a cone-degenerate operator. Actually, yeah. So. And so if you want to understand edge-degenerate operators, one has to understand this cone-degenerate operators first. This is what we are going to take. Tomorrow then tell you then more about this edge thing. Okay, so and then of course there's a compatibility condition if you have a couple of such symbols. They're not completely independent, yeah, so they belong to a certain space which can be intrinsically described, and then they have to be compatible, and it is here. So if you here freeze, so this pointwise, it is a pseudodifferential operator. It has a principal symbol, and that principal symbol you get so offset if you basically offset here x to 0. That's the it's not that important, yeah? It's just something to keep in mind, but it's not that important. So now comes the important thing. We also have, so we will learn if we have cone-degenerate operators, we have so-called conormal symbols. And the conormal symbols control the way in which asymptotics are mapped. So yeah, I give you a certain asymptotic expansion. I know the conormal symbols, and I can tell you what you get after you let this operator act. And so I will discuss it later. Yeah, but at the moment, just how they are defined, these conormal symbols you sort of do a Taylor expansion at x equals 0. You can get then here the x to the j and so on. We forget these, yeah, so we differentiate with respect to x j times, and you have this combinatorial factor, and then set x to 0. So what we get is a function depending on 3 variables, y, z, eta. The z we are going to learn that is the co-variable to x under the Manny transform from today. Yeah? At the moment it's just like that. And it is basically a smooth and y. I always have a b because I do a local analysis. Local analysis means on all of RD and everything stays fine. So that is sort of requirement. It has to be meromorphic in Z, a meromorphic function in Z, and it is then, as you can see, it is a polynomial of degree j in eta. And so whenever you differentiate this respect to x, once here you get out another eta. In total, yeah? Eta j components of that eta. So get a polynomial, yeah? So, and, well, suppose our operator possesses a transmission property, then one can prove that the A plus is edge-degenerate, and moreover we know the principal symbols. And that is the form of the principal symbol. So here we have smooth coefficients, we have a polynomial of degree j, so everything is fine. What's the important point is here. We have a quotient of 2 gamma functions. Yeah, and so basically gamma function, maybe. So this quotient, I explained later, this quotient is responsible that a Taylor of smooth asymptotics is mapped to smooth asymptotics. If you change this quotient, you can basically have other asymptotics here, which are mapped to something each other. So that was sort of the basic observation. So we know the conormal symbols, and they are of that form. Okay. More on that later. Good. I said basically the thing which was important was to come up with there were edge-degenerate or edge-Sobolev spaces before, but now we have them in the form exactly as needed over there. So this is what we do. Yeah, so near a singular point in the Fourier in the two-dimensional analysis, we place the Fourier transform as a Manning transform. It's just out of convenience. Yeah, the Manning transform is also Fourier transform, but for the multiplicative group R plus. Yeah, so that is like so here you see it. How is it defined? Here you have x to the z, and then you have here -1 means the invariant measure is dx over x. Yeah, so if you have here complex support, you get it for all complex. So you see, yeah, and then it is extended to certain classes of functions and distributions with the half-life. So what you're going to need is the inverse Manning transform is given by that. So you integrate along one vertical line, and that's because it occurs so often. These lines get a name. Gamma Gitter is the real part of beta. Yeah, so we have here such line. So we have the Manning transform. It's x to z, and then we have this line in the here complex Manning form. And this all is real equal to beta. Okay, and so then. If I have the Fourier transform, differentiation becomes multiplication by the covariable. Here we have a similar thing. Yeah? So we have this totally characteristic derivative with the correct constant, which is a minus here. It becomes multiplication by z. So minus x dx becomes z. And then we have also Plancherel. So we are going to work with weighted space as an x to the gamma. So standard L2 on the half line becomes the L2 on here this vertical line where the real part is 1.1. Yeah, so the standard L2 goes to the L2 on gamma 1/2. Okay, so the properties we're going to use. What's the time? Oh, I'm sort of slow. So, and then we expect, yeah, convolutional asymptotics of this form. So I will explain here this factor, this combinatorial factor later. So we have x to the p, and for some reason I write minus p instead of p, and then we have certain logarithmic terms, and then coefficients, say complex numbers. Oh no, I'm just explaining it here, yeah? And that is now another nice exercise. If you have such an asymptotic term, and you Manning transform it, you can read off the asymptotics after Manning transform in a pattern of poles. Yeah, we get so you have sort of some basic weight lines. Then things. Yeah, so basically you cut off things close to x equals 0. You don't care about what happens at infinity. Therefore, you get things holomorphic to the right of that weight line, and basically to the left you get poles. And the poles just is the one-to-one translation. It tells you exactly what your asymptotic terms are. And here's here's this relation. So writing minus p instead of p and having this factor here in front of everything, we get a pole of order not k, but k plus 1 at p. And this is basically the most convenient way to work with this stuff. Yeah, therefore the normalization here and not here. Yeah, and you get also here these our traces. Yeah, these coefficients are our traces, are going to be our traces. You also get them here, these coefficients. Yeah, so basically, having the poles, I know exactly what the asymptotic expansions are. And the proof is not hard. Yeah, you just so if there's no logarithmic term, you just compute this, and then you get the logarithmic terms just by differentiation with respect to p. And as I said here, yeah, because you cut off things close to x equals 0, the integral here from 1 to infinity. That's in the roll at this point. That is a translation. Yeah. If you have basically x to the minus p log to the k, you get a pole of order k plus 1. Yeah, exactly at p. Okay. So now actually now our functions also are going to depend on y, and then we expect asymptotics of that form as x goes to 0. Then here our potential traces also depend on y. So here I just simplify things a little bit. It's actually tremendous simplification, but that is what we are going to do here. Yeah? Consider only the relations. That is so-called constant asymptotics. Yeah, so if so we have here our z, and for one dimension we have y, so then we have basically the poles potentially can also depend on y. So we have here so potentially a piece which depend on y, and then also the number of the p's are in a sense this is a nonlinear eigenvalue, and then also their multiplicity. So the multiplicity of these nonlinear eigenvalues tell you how many logarithms you get. Yeah, and as you can see, if this is variable, we can have these crossings. Yeah, then we have branching of it's called branching of asymptotics. Variable asymptotics makes things much more complicated. Yeah, so we stick to this constant discrete asymptotics where we have just that's right. It's constant. Yeah? Also the multiplicity is constant. Yeah, and here's one example. Yeah, so if we do a Taylor series expansion at x equals 0, we just get this. Yeah, x to the L and a non-negative integer and certain coefficients. And if our u is in HS, then the coefficients are going to be in us minus L minus 1/2. That is another point. Here, so this asymptotic term is only a formal asymptotic expansion. We cannot write it that way because in general the coefficients are not smooth enough. And you see, if you take the first coefficient here, which is in HS minus 1/2, and you form the product, okay, the x to the L is fine, it's smooth, yeah, but your function will only be in HS minus 1/2, not in HS. Yeah, so these are sort of formal. We have to do something about that. But okay, that can be handled. Yeah, so we have here a constant discrete asymptotics, and we have to handle these asymptotic terms. Okay, good. So, but before we do that, we start with asymptotic types. So basically, we have fixed asymptotic expansion with p and k's, and yeah. So I told you what is such an asymptotic type. Well, the best way to say it, it is complex analysis. It is a divisor. It tells you, a divisor tells you about the zeros and the poles of a geomorphic function on Z. So we have basically here our zeros and poles, and they come with multiplicities. And okay, so here it is just a translation of that in case you don't know what it is. So we want to have a non-negative divisor. Our poles, so we always fix one basic conormal order delta. Our poles are to the left. Yeah? So then basically we have the places where they are. We call that that is sort of the board. I call that PCP, ICP. And so that is a discrete subset of C, which is to the left of that line. Yeah, and then and what is that? Then we have here numbers, MPs, this is multiplicities, and okay, and we want, yeah. So that condition is in every polygon thrive, you have only finite many of these poles. That is the second condition. And the last one is needed for coordinate analysis, not that important at the moment. And in the following, it is very convenient to write these asymptotic types as sets. So we take all pk, so p is the order of p, and here's some natural number of 0, where k is strictly less than mp. So mp is, if you go back here, you see that we get a k plus 1. So the NP is here, this is the order of the proof. Okay? So we make strictly yes. And here's an example. So if you do such a Taylor series expansion, that is the type you get. It's negative L, and non-negative integer, and the zeros, no logarithm terms. Okay? Okay. So now we want to define. Okay, so now we want to define our spaces. I'll show you the spaces we are going to define. Oh my gosh. These are the spaces I'm interested in, and we do it in 3 steps. So first off, we need some weighted spaces on here on our local model, which is a half space. And these are spaces HS gamma, so this is sort of weighted solar spaces. Here we have the total characteristic derivative, and we have an x to the minus gamma in front of everything. So that's the definition of S is a non-negative integer, and in general you get the spaces by duality interpolation. So here's a nice characterization. There are many such characterizations, but here's a nice characterization in terms of the Mellin transform. Suppose S is non-negative. Then you just take, here's a Mellin transform with respect to x. This is a mu depends on x and y. And so then basically here's a variable z. You take the RHS norm with respect to the y variables. Here you take the L2 norm, and here you put the corresponding weight. And if you have a gamma here, you integrate about this so-called weight like gamma. Yeah, that is. There are many such equivalent characterizations as well.
So the first norm is HS. Yeah.
This is HS.
No, in the integral.
The integral is the Mellin transform of.
Yeah, but that norm is HS.
That's the HS norm, yes.
And then you have.
With respect to the so the U tilde depends on Z and Y. It depends on x and y, then it does a Mellin transform, and then it takes the S norm with respect to y. I do the same. So basically, so here we have in total S derivatives. So here we have all the y derivatives, and here we have all the x derivatives. Yeah, and so basically x dx after Mellin transform becomes multiplication by z. Yeah, that is basically after heuristics behind. Good. Then in the following phi will always be such a cutoff function. Yeah, it is 1 close to 0, and it's 0 close to infinity. And then you want to have this, we call it K as gamma space, this H as gamma close to 0, and the standard HS far out. Then we fix some, that is not so important. So, okay. And then I want to handle these asymptotic terms. And the correct definition is this one. So here is the W is one of the PKs we had here in this asymptotic expansion. This is one of these guys. Yeah, and then times that one, I make it just, yeah, I start with the W and make it a function of x and y. And this is the way in which it is done. Now we have this factor in front of it, don't need to worry about that. So we take this cutoff function we had here on this previous slide, and so here now the argument becomes x times Japanese bracket of either. Either is a Fourier equivalent to y. We Fourier transform the w and put here the x minus b by k x. That is the correct thing to do. So for instance, if x is 0, then this is just 1, and you get just basically formally here, you get just this times w. That's what you want to have, right? So otherwise you see, because it is of bounded support, so for x positive, it is of bounded support with respect to either. We get for positive x, you get a smooth function, and also that is also of bounded support with respect to x. Okay? So, but if we are interested in this ks gamma spaces, and here's the answer. So we take w from hs on rd, and actually if a k is positive, we make this space a little bit smaller just by allowing here log k times either. Yeah, it makes it a little bit smaller, and then we get it. So basically, what we get is of a conormal order 1/2 and the real part of p, only that we don't actually reach it. Yeah, so we can have a positive epsilon and we get as close as we want. But there's a price to pay. So as closer we get, as more regularity we lose. So the regularity is s plus something. As better here the conormal order, as closer we get, as more we lose. That is one observation, and that is the correct thing to do. It's here by the second result. If you just form the difference with this asymptotic term we wanted to have, we have a sort of same sort of spaces, only that here this flipped over. This is now minus epsilon and plus epsilon. So we jumped after many transform from z half to z half. Yeah, but we are interested here in this first result. What's the time? Oh my gosh. I'm too slow. I am too specified. It's a school. Okay, so now that is the definition. So our spaces, these are the spaces. No, S. So we have some fixed. So we have the Sobolev regularity. For x positive, we have standard Sobolev spaces. Don't worry about that. So then we have this fixed conormal order delta. We have an asymptotic type, and then basically we have the length. We have some. So basically, we wanna get Fricke spaces, and we just observe asymptotics from here to here. Okay? So we have poles. Let's stop observing things here. And then it is always bad if a pole ends up on that line. But this case can be treated by interpolation. Yeah, here for general, we use interpolation. So we can assume here that this intersection. Yeah, so there's no pole on that line. We can assume that. By the way, if you have the standard Sobolev spaces, the half integers are exceptional. This is exactly this exception points here. Yeah? There's always where the number of boundary traces jumps. If s is less than 1/2, no boundary trace. If s is between 1/2 and 0/2, one boundary trace, and so on. It's exactly that phenomenon. So, and then basically these traces come with a certain regularity. You don't just need to memorize that. Yeah, it is just s plus v plus p plus delta minus 1/2. There's k here, and just if we subtract all this, so finally many of these things, so we get a better conormal order. So we move from here to here. Yeah, but the price we had to pay is just this regularity. This was just the observation here on that here previous page. Yeah, better conormal order, this regularity. Yeah, so then if we are in such a space and the UPK are unity determined, we just denote it with gamma PKU. And these are basically our trace operators in the calculus, essentially. Yeah, and then the case occurring most often in application is that S is a non-negative and zeta equals S. And then I just don't write the zeta. Okay? And we have spaces H as delta P. Okay, so here's an example. If you take a standard Sobolev space on the half space, that is just H as naught. And here we have our asymptotic type for the Taylor series expansion yet before. Yeah? Or another example, if you take this H as naught space, which is all distributions or functions in HS, and all R1 plus D, such as the support is contained in the half space, it's usually denoted that way. Just the same thing, conormal order is 0, and the asymptotic type is the empty asymptotic type, which means no asymptotic, no poles, everything is holomorphic. So all basically what we have done in the spaces, this is including also these correct traces, is we have just replaced the 0 here by some general delta. We have replaced that by some asymptotic P, which is different from P naught possibly. That's all what we have done. Otherwise, we have exactly the same spaces as before. Definition looks a little bit complicated, but this is actually what it is. Moreover, so I had the third condition in defining these asymptotic types I were not discussing, and this third condition just produces coordinate invariance, and then we also have the spaces on manifolds with bounding, say, compact. Okay? So, fine. Okay. The time is essentially up. Maybe I have 2 more exercises for you, and then I start. The first one is, yeah, so you have basically, I said you can characterize things with help of the Mali transform. So if you have basically functions, so this is your functions on the half line having asymptotics of type P, that's just easily introduce that space. And so as x goes to 0 goes to infinity, we have Schwartz behavior. We take the Mali transform, then we get something which is meromorphic on C with poles given by P. That is, we have poles at Z equals P of order at most empty and no other poles. And then, if we basically restrict to such vertical lines, we get Schwartz behavior. Yeah, and of course we have to cut out the poles. We take here some smooth functions, which is 0 close to the poles and otherwise 1. Yeah, so then along each of these lines we have Schwartz behavior. And so here's an example. So that is here. That is e to the minus x. It is a Schwartz function on the half space. It has a Taylor asymptotic, so it is an SP naught. Yeah, and the Mali transform is a gamma function, which has, as predicted, poles at exactly the correct places. So non-positive integers and simple poles. Now, this is now an example, and this basically that is here just a generalization of that, if you like, just for other analytic types. And another exercise is, oh yeah, we had this. Where did I introduce that function here? Here. Yeah, okay. I was so we just taking. So we have our Sobolev space for x large and this HS gamma space for x small. Then we have a function psi, which is x close to x equals 0 and 1 for x large. And then basically, if we multiply this by x to the row close to x equals 0 and we do nothing for x large, then we get exactly the other space with a shift of conormal order, and the asymptotic type is just P minus rho. And then we see a quick check that at least things with the regularity of the traces is correct. Yeah, so that should be such a statement. This is one of the first 6 that we check. That is fulfilled. Okay, thank you.
Are there any questions or comments?
expansions are formal, you said.
Yes, but
But nevertheless,
they become not formal if I do here's the correct thing, and the correct thing is to let this gamma pk act on these traces. That is non formal because these guys are in the correct spaces. Yeah, basically to explain things here, I write it. Where is it here? I write it that way. Yeah, but what actually is meant by that, I take a UPK and with a gamma pk in front of it. That makes it, yeah, we start with a function of y and get a function of x and y, and this is basically of that form. And that is shown here as a lemma. And so we have a certain regularity, and so if we subtract this guy, then that's basically good. That is what is, well, I mean, if you have, so if you go so if you have basically gamma naught, the trace operator from S R1 plus D is S minus 1/2 by D. So this restriction to x equals 0. So and this is surjective. How to prove that? You take a W here, so then here, and you do exactly what is written there. So you take F as a negative one, and then F x either or W and nothing more. This is x from the 0. Fine. It's exactly the same operator. If you take here basically the non-one trace, then you put here an x to the 1. It's exactly this operator, which is used. So there's basically nothing new. Yeah? The new thing is here to observe here these regularities. That is a longer computation I wanted to show, but then I decided not to show. Okay.
Yeah. Sorry.
Ingo, in slides 22, the expansion,
22.
you put here real part going to minus infinity, but
Yeah, because of the minus. You want to become basically things flatter as x goes to 0, which means the real part of minus p has to increase. This is close to x equals 0.
and then how you get the equilibrium, because k is going to infinity, and then minus p is going to plus infinity to,
P can, sorry, say again?
you said you have logarithm in order k.
Yes.
So as in order minus p, the real part will be
So what is meant by that? So that is still a formal description here. What is meant by that? So we start with some basic weight line after Milling transform. We improve things up to here with, between two such vertical lines. There are only finite manifolds. And then, of course, their multiplicities. Every pole comes with a certain multiplicity, or order. The poles are order, and this is it's non-negative eigenvalues with a multiplicity, and then of course this total multiplicity is also finite. This is what this means. Yeah, so basically, poles. So if you have a general thing, yeah, the whole meromorphic functions of poles can go everywhere. This is forbidden here.
But how can compensate this integrally? The denominator we have infinity, and down we have just k factor. The other term is going to infinity.
No, if this happens, yeah, that this or that goes to infinity, then the real part of p has to go to minus infinity. That is meant by that. Yeah, so if this here, if the k becomes larger, we have to move more and more to the left. This is meant. Yeah, so basically, between two vertical lines, only finite many poles. That is a condition. Yeah, so basically, adding more and more terms, things become flatter, flatter, flatter. Yeah, so the asymptotics is in terms of flatness. That basically thing. This is also what we have for Taylor asymptotics, right? X to the 0, then x to the 1, x to the 2.
Okay. Okay, so we thank Professor Witt again, and we resume at 2. And for lunch, there are no sandwiches, so usual options. There are sandwiches.
From yesterday,
From there.
but there.
Okay.
Yeah, no, 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 no,